Electrical. Civil. Chemical. Mechanical. Long ago, the four nations lived together in harmony. Then, everything changed when the chemical engineers attacked. Only the Avatar, master of all four engineering disciplines, could stop them. But when the world needed him most, he vanished. 100 years passed and my brother and I discovered the new Avatar, a mechanical engineer named Aang. And although his mechanical engineering skills are great, he has a lot to learn before he's ready to save anyone. But I believe Aang can save the world. We had finally reached our goal, the Northern Electrical Engineering Tribe. We had narrowly avoided capture from the chemical engineers at every turn. Aang presented himself in front of the elders and showed that he was the last mechanical engineer. After seeing firsthand that Aang was the Avatar, the elders permitted us to be trained as electrical engineers. We were to learn under the esteemed Professor Paku.
Always remember that engineering teaches us acceptance. Let your emotions flow like current. Today's lesson will be about DC converters. A DC to DC converter is a power electronic circuit that efficiently converts a direct current from one voltage to another voltage. Without a doubt, DC-DC converters play an integral role in modern electronics. A power converter is a device that converts one form of energy into another on a continuous basis. There are several such devices available with varying degrees of complexity, reliability, and performance. Power conversion mechanisms can occur in various forms. A DC-DC converter is an electronic circuit that facilitates the conversion of direct current from one voltage level to another based on the requirements. This electric power converter is capable of operating at a wide range of power levels from very low power to extremely high power. DC-DC converter circuits employ high-frequency power conversion using switches and other passive components to eliminate the switching noise, thus regulating the output voltage. The arrangement of the energy storage elements is determined by the step-up or step-down requirement. The basic idea is that the inductors and capacitors employed in the circuit should form a low-pass filter network in some manner. This helps to minimize or eliminate the possible superimposition of AC ripple or other components with the output voltage formed due to switching action. We will analyze our converters first in a basic level. Know that the example I'm currently showing you is a buck converter, but the analysis we will review will be applicable to other converter types. The input to a DC-DC converter is an unregulated DC voltage V. The converter produces a regulated output voltage V, having a magnitude and polarity that differs from VG. For example, in a computer offline power supply, the 120V or 240V AC utility voltage is rectified, producing a DC voltage of approximately 170V or 340V, respectively. A DC-DC converter then reduces the voltage to the regulated 5V or 3.3V required by the processor ICs. High efficiency is invariably required since cooling of inefficient power converters is difficult and expensive. The ideal DC-DC converter exhibits 100% efficiency. In practice, Efficiencies of 70% to 95% are typically obtained. This is achieved using switched mode, or chopper, circuits whose elements dissipate negligible power. Pulse width modulation allows control and regulation of the total output voltage. This approach is also employed in applications involving alternating current, including high-efficiency DC-AC power converters, AC-AC power converters, and some AC-DC power converters. Now let's break down this converter circuit to understand how our converters work. A single-pole double-throw switch is connected to the DC input voltage VG as shown. The switch output voltage Vs is equal to Vg when the switch is in position 1 and is equal to 0 when the switch is position 2. The switch position varies periodically, such that Vs is a rectangular waveform having period Ts and duty cycle d. The duty cycle is equal to the fraction of time that the switch is connected in position 1, and hence d is greater than or equal to 0 and less than or equal to 1. The switching frequency Fs is equal to 1 over Ts. In practice, the SPDT switch is realized using semiconductor devices such as diodes, power MOSFETs, IGBTs, BJTs, or thyristors. Typical switching frequencies lie in the range 1 kHz to 1 MHz. The switch network changes the DC component of the voltage. By Fourier analysis, the DC component of a waveform is given by its average value. The average value of Vs of t is given by the equation shown. The integral is equal to the area under the waveform, or the height Vg multiplied by the time dTs. It can be seen that the switch network reduces the DC component of the voltage by a factor equal to the duty cycle d. The DC component of Vs is less than or equal to Vg. The power dissipated by the switch network is ideally equal to 0. When the switch contacts are closed, then the voltage across the contacts is equal to 0, and hence the power dissipation is 0. When the switch contacts are open, then there is 0 current, and the power dissipation is again 0. Therefore, the ideal switch network is able to change the DC component of voltage without dissipation of power. But as we know, that's a false dream. In addition to the desired DC voltage component Vs, the switch waveform Vs of t also contains undesired harmonics of the switching frequency. In most applications, these harmonics must be removed such that the converter output voltage V of t is essentially equal to the DC component V. The buck converter we are analyzing contains a single-section LC low-pass filter. The filter has corner frequency F0 given by this formula. The corner frequency F0 is chosen to be sufficiently less than the switching frequency Fs, so that the filter essentially passes only the DC component of Vs of t. To the extent that the inductor and capacitor are ideal, the filter removes the switching harmonics without dissipation of power. Thus, the converter produces a DC output voltage whose magnitude is controllable via the duty cycle D using circuit elements that ideally do not dissipate power. The conversion ratio M is defined as the ratio of the DC output voltage V to the DC input voltage Vg under steady-state conditions. For the buck converter, M of D is equal to the duty cycle D. These equations are valid in steady state. This figure illustrates one way to realize the switch network in the buck converter, using a power MOSFET and diode. A gate drive circuit switches the MOSFET between the conducting and blocking states, as commanded by a logic signal delta of t. When t is between 0 and dTs, delta of t will be high. When delta is high, then MOSFET Q1 conducts with negligible drain-to-source voltage. Hence, Vs of T is approximately equal to Vg, and the diode is reverse biased. The positive inductor current IL flows through the MOSFET. At time t equals dTs, delta of T becomes low, commanding MOSFET Q1 to turn off. The inductor current must continue to flow. Hence, IL forward biases diode D1, and Vs is now approximately equal to 0. Provided that the inductor current IL remains positive, then diode D1 conducts for the remainder of the switching period. Since the converter output voltage V is a function of the switch duty cycle D, a control system can be constructed that varies the duty cycle to cause the output voltage to follow a given reference input. This figure illustrates the block diagram of a simple converter feedback system. The output voltage is sensed using a voltage divider and is compared with an accurate DC reference voltage VR. The resulting error signal is passed through an op-amp compensation network. The analog voltage Vc of T is next fed into a pulse width modulator. The modulator produces a switched voltage waveform that controls the gate of the power MOSFET Q1. The duty cycle D of this waveform is proportional to the control voltage Vc. There are several types of DC converter topologies that have different characteristics based on variations in their circuit designs. The type I have been showing examples of is a buck converter. The buck converter reduces the DC voltage and has conversion ratio M of D equals D. During operation, the input voltage is connected to the inductor, and the difference between the input and output voltages is then forced across the inductor, causing current to increase. During this time, the current flows into both the load and the output capacitor, charging the capacitor. When the switch turns off, the capacitor discharges into the load, contributing to the total current, the sum of the inductor and capacitor current being supplied to the load. Buck converters are essential in systems that use distributed power rails, like 24 volts to 48 volts, which must be locally converted to 15 volts, 12 volts, or 5 volts with very little power loss. Think of it as a step-down DC transformer. Conversely, a boost converter takes a DC input voltage and produces a DC output voltage that is higher in value than the input, but of the same polarity. When the switch is turned on, the input voltage is forced across the inductor, causing the current to ramp up. When the switch turns off, the decreasing inductor current forces the switch end of the inductor to swing positive, forward biasing the diode and allowing the capacitor to charge up to a voltage that is higher than the input voltage. During steady-state operation, the inductor current flows into both the output capacitor and the load during the switch-off time. When the switch is on, the load current is supplied only by the capacitor. This allows the boost converter to produce an output voltage V that is greater in magnitude than the input voltage Vg. So think of it as a step-up DC transformer. Its conversion ratio is M of D equals 1 over 1 minus D. The buck-boost converter is a type of DC converter that can produce an output voltage that is either higher or lower than the input voltage, making it a versatile power topology for various applications in power electronics, where input voltage regulation and output voltage requirements may vary. The buck-boost converter operates in two distinct modes: the buck mode, where the output voltage is lower than the input voltage, and the boost mode, where the output voltage is higher than the input voltage. The final topology to discuss is the Chook converter. The Chook converter contains inductors in series with the converter input and output ports. The switch network alternately connects a capacitor to the input and output inductors. The conversion ratio M of D is identical to that of the buck-boost converter. Hence, this converter also inverts the voltage polarity, while either increasing or decreasing the voltage magnitude. In conclusion, the different topologies serve different functions depending on need. Now let's meditate on the engineering I have shared. DC converters are essential electronic circuits that play a critical role in modern power management systems. Their primary function is to convert the voltage of a direct current source from one level to another, ensuring stable and efficient power delivery to various electronic devices.